Awesome. So I'm going to share my screen here, but before I do that, I'm going to have to drop off. So I'll put my email in the chat. If you have questions on what I'm about to talk about, just go ahead and send me an email. Can everyone see my screen?
Yes.
Awesome. All right, so just a little bit of background on EPIC and the UFS and kind of the vision behind it. So this actually started several years ago with a conversation that I had with Bill LaPenta and Fuqing Zhang. This was when Bill was over at NCEP, and we were talking about the idea of being able to get people in the community to be able to run the code, because there was a lot of interesting, innovative ideas that were bubbling up in the community at various universities and private industry and even other government agency labs. But the problem was no one had access to the code, and a lot of the code was really hard coded for NOAA's own HPC systems. And so even if you gave someone the code, they weren't really going to be able to run it anywhere. And so the idea was, let's figure out how to refactor all this code so it's largely hardware agnostic. You can run it on anywhere from commercial cloud to laptop, wherever. And then let the community test their own ideas on how to improve various things, and then share those back with EMC and NCEP. So we drew this out several years ago on a napkin. And then when I came to NOAA, Bill actually drew out what we had on the napkin on an ink board, and I took a picture of it. And this is kind of the vision. This is a couple of years ago, but it's surprising to me how well we've stuck to this. But what I really wanted to talk about here is what Bill has here: people, process, and product. So the people, that's everybody, that's the community. And the process is, how do we empower the community by putting the code out there and giving people access to various compute architectures to test their ideas on. And that's not just the process, but that's also the product. So I'm excited about what we're going to talk about today, because this is sort of the first step in, we have to refactor all this code and then putting it out there. And when we just put it out on GitHub's not really going to solve the problem. We have to train everyone and get everyone comfortable with, familiar of how to use that. So why is cloud interesting? It's really the appeal is particularly on the research and development side. For example, if you're actually running HPC for an operational center and you're using it at 90-some-odd% capacity 24 hours a day, whether you own that hardware or you lease it or you're doing it in the cloud, it's about the same. But on the research side, when the need for compute research varies wildly with the amount of experiments you want to run, being able to do a lot of experiments in parallel by surging outward, in other words, just going and getting access to more nodes, you can do that. And the cost is the same, whether you're running these experiments one after the other or all at the same time. And so you can get a lot of work done a lot faster if you can sort of surge outward. One of the challenges at the Weather Service is there's just more innovative ideas in the community than they can possibly test or implement. They're constrained by on-prem compute, by personnel. There's a lot of ideas, and it's not like they're not aware of these. It's just a matter of they're limited in their ability to test it. So one of the easiest ways to solve that problem is just enable the community to test their own ideas. So they're coming back to EMC and NCEP with results versus just an idea that hasn't been tested. Like I was saying, there's a long queue to run experiments with the on-prem systems at NOAA. So if you take a look at these two plots, on the right, you'll see ECMWF's research versus compute. So this light blue here, this is what they have for research. It's roughly about 5 times as much as they use for their operational compute. If you look over here on the left, the orange and the blue, this is WCOS2. So this is the production system, or the soon-to-be production system at the Weather Service, and their backup system. So that's our operational compute. versus everything they have for research computes, which is, you could argue, is either a 1-to-1 or a 1-to-2 ratio. So they're way behind on what they need on research compute with respect to the operational system. So the hope is that we can make up the rest of this gap with access to the commercial cloud service providers. And the interest there is that it's scalable, it's on demand. When you want to run experiments, you do have to pay to use it, but when you're not running experiments, you're not paying for power and cooling and floor space, leasing in a data center and all that. And you can, if you actually are running experiments where they're not necessarily wall clock time sensitive, you can run these in the off hours, nights, weekends, and you can get cloud compute for pennies on the dollar. From what I've seen so far, what I would refer to as antibodies to transitioning over to cloud, it's largely cultural. It's not technical. This is we've proven that you can run all this stuff in the cloud. It's a new thing. It's different. There's a little bit of fear of the unknown, but part of what we're going to be doing with these courses is taking people through this, because it's not as complicated and as intimidating as you might think. But we do need to be careful. So you will see some of this code when we want to try to port it back and forth between cloud service providers. You may or may not end up in situations where you're not using a lot of the cloud native tools provided by that particular vendor. And that's probably a good idea, because you don't want to get stuck in what we refer to as vendor lock, where you're tied into using only one cloud service provider. If we can keep these tools sort of agnostic enough to the particular cloud service providers, it's going to drive the cost down through competition. So this is kind of the overarching vision of where this is going. So let me start with the far right, or the back end. So there's the big data project. Cloud service providers host a lot of this output. So things at NCEI, a lot of this real-time operational output, the non-real-time research stuff, various archives, a lot of this is being transitioned over to cloud. And on the front end, we've got a lot of the data, probably in the near future, most of the operational data sets, which are traditionally shared over the WMO's GTS, will eventually be mirrored into the cloud. I know that NESDIS has done a tremendous amount of work in doing a lot of their satellite pre-processing data in the cloud. The conventional data is probably a little bit of an easier lift. But we've got the data that you would use to initialize the model. And then the only step in the middle is really the NWP step, which is the data assimilation, running the models, and doing the post-processing. So the reason why this is important is you can save a lot of time and a lot of money if you stay in the cloud the entire time. But if you get in a situation where you're downloading and uploading, you're going to get hit with egress charges and things like that. So it's not just saves time, but it also saves money to just do the entire start to finish process of producing and running models. So this isn't just a great idea, this is also the law. So here we have the NITIS reauthorization of 2018, and in there's two important aspects to this. So under Section 4, which is the authorization of the Earth Prediction Innovation Center, or EPIC, which is why we're here today, there are the Section A and Section B, leveraging the weather enterprise, that's you, and enabling scientists to collaborate. So that's sort of what the basis for all this is. And then we have over here in E, create a community global weather research modeling system. So that's the unified forecast system that's accessible to the public. So just saying I'm going to tar up all the code and stick it on GitHub is not enough. It's got to meet basic end user requirements for running on systems that are located outside of NOAA. So this is critical for us to solve this problem, not just because you can't necessarily have code that's specifically hard-coded towards NOAA machines, but one of the other limiting aspects for NOAA R&D was that unless you had a security clearance, you weren't going to be able to log into their machines anyway. So this really opens a lot of doors for the external user community. And down here in part 3, try to use as much different computing capabilities as you can, including cloud-based capabilities. So this does actually present a little bit of a challenge, which is what happens when we put all this code out there and the community starts testing ideas and coming up with some interesting results. Then what? How does that find its way back into NOAA? So this is not a new problem. People have been writing about this research to operations challenge for years, and it's referred to the valley of death as a good reason. It's because a lot of really good ideas that happen in the research community never make it to operations. And it's not because it wasn't something that was going to be very successful. There's all these other steps in here to do a proper transition. And our hope is that if we design this funnel right, and this is one of the original versions of the funnel by Louis Uccellini and Sandy McDonald, which is, from back in 2006. If we do this right, we will be able to figure out which ideas are really going to have the biggest return on investment and bundle them into operations. But this is the original version of the funnel. I've redesigned it a little bit, and I'm going to share that with you today. So this is from my BAMS paper last year, which is basically talking about this. Over here, one of the things that I've added to this funnel is not just your typical DA and physics and coupling, but also software optimization and observation. So if we put the DA system out there, it allows commercial data providers to do impact optimization and impact tests with their own observing system. So no longer does a company who produces some type of observation, whether it's a CubeSat company or some sort of commercial in situ observation, they don't necessarily need to go to NOAA and say, hey, why don't you test the impact of our observing system in your model? NOAA can say, here's all the code and it runs on any compute you want, test the impact of your own observation and come back with results. So that is actually really efficient. It also, down here, the software optimization, this is a critical point because a lot of these innovative ideas, and I'm speaking for myself here as a scientist, I don't write very efficient code. And maybe my idea works, but if it increases the runtime or causes instability later downstream, there's going to be problems. So we do have various off ramps here. So this is maybe not a candidate to go to the next step. So we've got these stages and gates, and the criteria for each one of these gates is going to be determined by a community modeling board. The important thing is that everyone knows what criteria they are going to be judged on in advance, because things will get kicked out of the funnel at some point. But my hope is that everyone feels that the process was fair and everyone knew what they were going to be evaluated on. When you get far enough down the funnel, there will be a go, no-go decision on what would be a candidate for operations. So crossing this threshold would mean, okay, this is actually something that is of interest to INCEP to get bundled into one of the future operational releases. Down here, it becomes probably more of a software engineering and scalability efficiency challenge versus just a straight up science challenge. But there will be everyone in all three sectors involved in this entire funnel. And if we sort of turn that funnel up on its end, this is what it looks like. So I'm going to take you through sort of a vision of the process. And this is a sort of a circular process here, but I'll just start with EMC. So we start with EMC. They're the ones who hand off the operational code to NCO, but they're also working with the folks in EPIC to bundle these public releases. So taking this code and making it user-friendly to whatever compute architecture the community wants to run it on and placing it on GitHub. And this is the community, this is you, this is academia, industry, everyone who wants to take this publicly available code and run it and create and test their own innovative ideas. This is all happening on various compute architectures. Today, we're going to be using the cloud, but you could test this out on all sorts of different architectures. And then if you come up with interesting ideas or ways to improve things, whether it's some type of efficiency or some type of improvement to a various parameterization or just a new observing system that you wrote an observation operator for, you can put it into the funnel and test it out. And you can test it out against the full suite of real-time observations. So you know what you're looking at as far as initial conditions. If it needs more research, it can get kicked back into the community. If it needs more optimization, it can stay down here and be further optimized. At some point, here's that go, no-go decision for whether or not it's going to get bundled into something that's going to head back to the production system. But there are a lot of innovative ideas that the research community is interested in that will stay in future releases, but they won't necessarily be coming through EMC because they might not be part of the operational code. But this is research code that the scientific community is interested in. So what's in it for NOAA? They really get to leverage the broad expertise across the weather enterprise, universities, companies, other international centers. This also streamlines the R to O process and creates a common code base. So there's two sort of parallel threads here. One is the unified forecast system, which is transitioning the sort of complex production suite that NCEP has historically had, because they have to run so many different models to support mission requirements at different timescales, to a common code base with a lot more common shared libraries. That's one aspect of where they're trying to go with the UFS. The other parallel aspect of this is make it user-friendly to the broader community. And then empower them to actually run it and test it and come back with ideas. Here we also have, we're creating a situation where private investment is going to be aligned with the public mission. So if everyone's working off the same code base, if you're a private company and you want to download and run the UFS to support your clients, you're still going to be a user and an optimizer of this code. The added benefit here is it does eliminate that us versus them. Sometimes you see in the private industry feels like they're competing with the Weather Service, but now we're on the same team. We're working on the same modeling system. Part of this community engagement and outreach actually doubles as training and recruitment. So one of the things, if you're a company looking to hire someone, or you're the Weather Service or OAR, looking to bring on someone who understands NWP, chances are they've been working with this code, they understand it. They're not going to have to all of a sudden learn a new modeling system on day one at a job. And then a lot of times what happens with Congress is they're interested to see what private industry thinks. So advocacy from the private sector to Congress is going to generate additional support, which translates into more bigger budgets, more federal support for the federal agencies, which then turn around and use that investment to support the broader community. So what's in it for academia? Researchers get to contribute to the operational system. So not only do they get to run code, do experiments, if their experiments are producing successful, innovative ideas, their actual improvement can get bundled into a future operational release of the production forecasts that the Weather Service use. The funding opportunities not just benefit research, but also education and the public at the same time. So this kind of ties in down here with a lot of interest for the National Science Foundation. Because the code base is a common code base, one of the things that I hope that we get out of this is not just using the UFS as a research tool, but also a teaching tool. So there's a lot of ways you can run scaled down versions of this modeling system, of the DA system. If you are a professor and you're teaching NWP as a class, this will be the great tool to use in your lab. So we're developing some coursework for this, some curriculum, some prepackaged lesson plans. All that's yet to come, but I think it's gonna really open some doors and create some opportunities at departments that have NWP as one of their graduation requirements. There's also multiple entry points into the development process. So when we have something like hierarchical system development, you can test various aspects of the model. It's not a system necessarily where you have to run the entire system from start to finish to test one small optimization to a certain component of the model. And like I said, now foreign nationals can work on the production code. So historically, they have not had the opportunity to log into NOAA machines. And now we open the door to get access to a lot of international expertise that gets to do development work on the code. And what's in it for industry? Better forecast for better products and services. So if you're in the private industry and you use either forecast output from another private company or the forecast output produced by the National Weather Service, in both cases, you're going to have better products and services because they have better forecasts. But it also allows you, if you're in private industry, to be more creative and optimize the model. If you're running a model that's specifically configured for your customers or clients' needs, you'll have a lot more flexibility and a lot less operational cost and overhead in running this in real time. And then, of course, government investment, it spurs innovation, but it's consistent with the market direction. So a lot of when I refer to market direction is particularly with respect to chips and compute. We really want to get aligned with where the broader chip and compute architectures are going, and being able to do this in an innovative way with the community coming along with us is, I don't really see another way to do it, to be honest. Forecast so let me just bundle the last couple ones. So if you're in the weather enterprise, you're a private sector company, obviously this makes sense to you, but almost every company that I've ever run into has a weather sensitive component to their business, whether they realize it or not. So let's just say the economic benefits of improving numerical weather prediction are going to go well beyond just the weather enterprise. This is going to benefit the entire economy. So that's what I had to present today. I will, like I said, I'll put my email in the chat, and feel free to just shoot me an email with some questions or thoughts or comments. And in the meantime, just thanks for being a part of this. We're going to be relying on you going forward.